Hey guys, Miss B again. I'm going to do part 2 of the periodic trends video, and this is all about the trend atomic radius. So here's some learning targets that will apply to the next few videos, defining what the periodic trends are, comparing and contrasting the trend for two elements, and then knowing what the patterns are and being able to explain them across a period and down a group. So it's probably a little bit important, I would assume, to know what a periodic trend is. But I'm using the word trend to replace pattern. It's basically a pattern, and we know that patterns exist based off the periodic table. So a lot of times I don't really need to look up minor details like the numbers or the statistics for an element, but I can use these trends to predict an element's properties quickly. I'm a fan of baseball, so think of this as like instead of looking up, I know for those of you who follow baseball, like launch angles are very popular lately, or those spray charts because there's been shifts happening. So instead of having to look up all of those little details of a hitter, what is their launch angle or their average launch angle, what percentage of the time do they hit ball to the right side, things like that. It's kind of like the patterns for the hitters. So maybe I just look at their batting average or the amount of home runs they have. So periodic trends are like a quick way to get some information about an element and kind of predict what might happen instead of having to dive deep and crunch a bunch of numbers. Okay? These patterns on the periodic table happen because of similar atomic structures with elements in the same group, in the same column, or some patterns or properties that we see in the same period or row. Okay, there are four main trends or patterns that we're going to talk about in these next videos: atomic radius, electronegativity, ionization energy, and electron affinity. This video, though, we are going to focus solely on atomic radius. This one, in my opinion, is the most important because if you really understand atomic radius and know how to explain it, you can kind of use the same ideas to explain the other three. Okay, so we're going to spend a little bit of time going through atomic radius. So the definition, that was one of our learning targets, like what is atomic radius, is the definition of the atomic radius is the size of the atom, and how we measure it is the distance from the nucleus, so this is where we have our protons and our neutrons, to the outermost electrons. These are the valence electrons. So we're measuring that distance. The reason it's called atomic radius is you guys are used to seeing circles in geometry. The distance from the center of the circle to the edge is called the radius. So that's where it gets the name from. If we're actually going to get measurements of these, again, we're looking at patterns. So not necessarily, like I probably won't ever show you numbers, but the unit we would see is picometer, which just is like very, very small because we know atoms are so small we can't even see them with our eyes. You might hear me say that there's a large atomic radius. That means the atom is big in size, or a small atomic radius means the atom is small. I kind of use all of those interchangeably. What's the size of the atom? Big, small, we're talking about the atomic radius. All right, so I think about dog walking a lot when I tried to figure out the patterns for atomic radius. So we have a dog walker here. He's got a lot of dogs. They're way better behaved than my pup Phoebe Buffet is on a leash, but we'll just assume that they were being good for this picture. Okay, so what I want you to picture is this guy in the middle. Actually, we'll do this. This guy right here is the nucleus. So he's my protons. All of the dogs are electrons. Okay? So let's just pretend for a second, I know this is a flat picture, but the dogs can go all the way around, right? He could have dogs in theory back here or in theory up here based off how their leash is. The dogs can travel in a circle around him, right? As long as their leash will allow. So right now what I'm seeing is we have some dogs, this guy and this guy, very, very far from him, right? Those are the farthest out as opposed to the electrons of the dogs that are closer. So the distance from his feet, or him, to that outermost dog is the atomic radius. For example, when I walk my dog, Phoebe Buffet, That's hilarious. I never wear, well, I wear dresses sometimes, but not skirts, but just go with it. Okay, there's me walking little Phoebe Buffet. And I have Phoebe on a pretty normal size leash because Phoebe likes to chase rabbits and squirrels and other things. Okay, my brother Blake, on the other hand, has a dog named Mac after Khalil Mack for the Bears. Okay, also a black and white dog. But Mac can be on one of those extendo leashes, right? Really far away. So Mac can travel way farther. Oh, wow, Mac has a lot of feet. Okay, and Mac has one black ear. So Mac can travel very far away. So looking from Phoebe and Mac, you can see that this is a larger atomic radius or a bigger atom, because there is more distance between Blake and Mac than there is between me and Phoebe. So how can I connect this to the periodic table? Because clearly there's nothing about dogs and leashes on the periodic table. The first thing I want you to think about is if we are in, let's look at this guy. If we are comparing two elements in the same group or column, so let's do lithium, sodium, potassium in the same column. I want you to think about the row numbers 2, 3, 4 as the length of the leashes, okay? So we're talking about guys in the same group. So I want you to think of lithium as a dog walker, walking a dog on a short leash and walking a dog on a little bit of a longer leash. Okay? Then I want you, I wonder if I can take this. That would be the dream. Oops, that was not what I wanted to do. Decapitated that guy on accident. Let's see. Okay, I give up. Sorry, guys. Then let's look at sodium. He's going to be someone walking a dog, but he has a short leash, a medium-sized leash, and a dog on a really long leash. And again, these pups can go all around, right, in a circle, but at the end of the day, the dog can only travel as long as the leash. Same thing with potassium. Here's my dog walker, short leash, medium, long, extra long. So what we see here is as we go down, the more energy levels, the more rings, 4 rings, that's like having a dog on a 4th size leash, right? So the bigger the radius. So as we go down a group, potassium has more rings, more distance, so it's a larger radius. Remember Coulombic attraction, right? More distance, less attraction. So this green guy, like potassium, has less attraction to this dog because it can travel so far. Blake can let Mac kind of wander because he's a well-behaved dog, whereas I need Phoebe much closer to me because she's not as well-behaved. Okay, the other option, what if we have 2 people walking dogs and we have the same length leashes? So what if I have, like, we'll do something easy. Aluminum, phosphorus, and chlorine. We got some elements in between, okay? But here's, at the end of the day, here's what we have. We have 3 rings. So I have 3 different people that look just like this. Nope. Like this situation, right? 3 different size leashes. But the difference is, yes, I have 3 dog walkers with leashes on, or dogs with 3 size leashes. So short, medium, and long. I'm like these guys, right? Lots of different size leashes, lots of different dogs. But what happens is we look now at muscle, how strong the person is walking the dog. Aluminum has 13 protons. Phosphorus has 15 protons. Chlorine has 17 protons. I want you to think of protons as like pounds of muscle strength. So let's look at these guys. Let's pretend that this girl here is aluminum. This guy is chlorine. Okay, I'm making a generalization assumption. I know women can be stronger than some men, but let's just kind of go with the assumption that maybe this guy's a little stronger. The reason this guy is stronger is he has 17 pounds of muscle in his arms, and this girl only has 13 pounds of muscle. If you were about to hire your dog, who is maybe not very well behaved, who would you trust to control your dog in this situation? Well, I personally would rather have this guy walk Phoebe Buffay because he's stronger. So what can he do? He can say, hey, and he can yank on those leashes and pull the dogs closer. So what they both have the different size leashes. So we have 13 protons, 3 size leashes. So 3 rings of electrons, 3 energy levels, 17 protons, 3 rings for electrons. But what happens is because we have more Coulombic attraction, more protons, this atom with 17 protons, these outer electrons here can get hugged in a little bit closer. So I want you to picture this atom with more protons actually getting squeezed in tighter because there's more control over the dogs. Does that make sense? You can't answer because this is a video, but hopefully it does. So it kind of feels backwards. Your instinct is probably like 17 protons, more protons, bigger. But I want you to think of it as a stronger person in the middle, pulling those dogs in a little tighter. He's not making the leashes shorter. He still has 3 different size leashes, just like the 3 rings for 13 protons. But I would be walking if I had all those dogs. My arms would be outstretched. I'd be pulled in one direction and the other direction, right? These electrons are stretching as far as they can go. Whereas more muscle, more protons can kind of say, hey, and pull those dogs in a little bit tighter. So more protons, as long as there's the same length leashes, more protons, more Coulombic attraction, which means smaller atom. All right, for those of you who are sick of my metaphors and just want to know how to explain this, because probably not going to talk about dogs on a test, or if you take college chemistry, hopefully this kind of clarifies. This is the pattern, okay? This is not a way to explain on a test, this first bullet point. This is the trick, I'll say trick or pattern to help you remember, but we're going to do the why explanations on a test or in a lab, okay? So here's the general pattern. From left to right, across a period, we get smaller. Okay, why does that happen? We add protons. Okay, so let's do across a period. That's this guy. We'll do some color coordination here. Let's do green. Okay, so across a period, we have the same number of rings or energy levels, same number of leashes, but as we move from one to the next, we're adding protons, which means there's higher Coulombic attraction. The electrons are pulled closer to the nucleus. Like that guy with 17 protons, 17 pounds of muscle. Hey, he pulls those dogs in, and that results in a smaller atom. Okay? When we go down a group, so as we go down, for comparing elements in the same column, the size or the atomic radius gets bigger. Why? Here's the down the group. As we go down, we add rings or energy levels, so that's longer leashes, which means there's more distance between the valence electrons and the nucleus, which makes it larger. So no matter what, if I'm in different columns, I'm gonna be bigger if I have dogs on longer leashes. If I have 5 size leashes and someone only has 2 size leashes, I'm automatically bigger no matter how strong I am. There's nothing I can do about it. Okay, so as we go down, that's gonna be our kind of deciding factor. More energy levels, more rings, that's bigger. But if there's a tie for the number of rings, then we're going to look at protons. So this is just for you guys to label. So as we go, let's see if I can. As I go across, we're going to get smaller. So the atomic radius decreases. And as we go down, atomic radius increases. Okay, so that's kind of our general pattern. So with that in mind, I kind of erased a little bit. I like to think of big fat francium and little bitty tiny helium. All right, so we defined the periodic trend, atomic radius, size of the atom. We talked about how to justify the properties, and now let's actually compare and contrast two different elements, that third learning target we needed to cover. Okay, so which has the larger atomic radius? My first strategy is, and I know it seems obvious for atomic radius, but it won't be so obvious with newer words like ionization energy. So what I like to do, even if it feels obvious, is tell myself what this means. So larger atomic radius means they're looking for the bigger atom. Okay? So I like to kind of just make a list of the useful information. So let's say the energy level is like kind of a more accurate way to describe it, but really I'm talking about the number of rings, what row they're in. So first I'm going to find calcium. Calcium is in the fourth row of the periodic table, right? 1, 2, 3, 4, fourth row down. So that means it has 4 rings, or it's in the 4th energy level. Now let's find barium. Barium is in the 6th row of the periodic table. Okay, the next thing we look at is protons, the number of protons, but I'm only going to look at the number of protons if it's a tie. So 4th and 6th is not a tie, so I'm not even going to bother with protons because that might just confuse me. So what's really happening is I have calcium walking dogs on 4 size leashes, 1, 2, 3, 4, and I have barium walking dogs on 1, 2, 3, 4, 5, 6 leashes. Who's going to be a bigger radius all the way around? That's going to be barium, bigger atom. So how do I justify? Barium is in the 6th energy level. Calcium is in the 4th energy level. This guy has more distance between nucleus and valence electrons, therefore larger atom. All right, I want you to pause the video and try this problem, and notice it says justify. On that last slide, those black bullet points, that was my justification, what I would write on a quiz or a test. I want you to do that for this one. So pause the video. All right, so larger atomic radius, that means we're looking for the bigger atom. So I kind of set up my little summary chart. SR and iodine are both in the 5th row, so that means they're in the 5th energy level, or they have 5 rings around them, around their Bohr model. So now it's a tie. So when it's a tie, then we have to look at the protons. So we did not do that in the last one because it was not a tie, but now it's a tie. And so my instinct is that 53 protons is bigger, so that must be the bigger atom. But remember, I am comparing two things, two people, both of which are walking 1, 2, 3, 4, 5 dogs on 5 different leashes. 1, 2, 3, 4, 5. So really the distance between, like the length of the leashes is not changing. So what we look at is the pounds of muscle. So this guy has 53 pounds of muscle. This guy has 38 pounds of muscle. I'm looking at the strength of the nucleus, the strength of the magnet. So who's going to have an easier time saying, hey, and pulling those dogs in, reining the dogs in, maybe pulling them just a little bit tighter, right? Pulling them in a little closer. That's going to be this guy. So he's going to be smaller because there's more attraction between the dogs and that strong nucleus. So who's going to be larger is strontium because there's less control. Picture Miss Beller trying to walk 5 different dogs on these long leashes and keeping them in control versus like a muscle man trying to walk these dogs. So now let's justify. So here's what I would say on a test. I would say both SR and iodine in 5th energy level. SR has 38 protons and I has 53 protons. SR has less Coulombic attraction to the valence electrons. Therefore, more distance between SR's nucleus and valence electrons, which means larger atom, which means bigger atomic radius. Okay, let me just read this over, make sure it makes sense. Notice I'm talking about both. Strontium and iodine are in the 5th energy level. Strontium has 38 protons, iodine has 53. Strontium has less Coulombic attraction to the valence electrons. More distance between strontium's nucleus and the valence electrons means it's a larger atom. Yep, that makes sense. All right, last one. Pause this video for me. I want you to try these ones on your own. All right, hopefully you pause the video. So, copper versus silver. I looked at the row, the energy level. Copper's in the 4th, silver's in the 5th. I did not need to look at protons because there's not a tie here. And so automatically the one with the bigger energy level, that's more rings, right? More longer leashes for the dog. So that makes silver the largest atom. The next one, copper versus krypton, both are in the 4th energy level, the 4th row, so I have to look at protons. Copper has 29 protons, krypton has 36, so this means that krypton has more muscle, in its nucleus, so it's able to pull those electrons, kind of squeeze or hug them in a little tighter, so it's actually smaller than copper. Remember, if we are looking at 2 elements in the same row, like copper and krypton, what we're looking for as we go across, these guys are going to be smaller, bigger on this side because these guys can kind of squeeze in those outermost electrons. This guy has less muscle, so it's going to be a bigger radius. Hopefully that helps with the first and most important periodic trend.